start off by giving a bit of an introduction to Filtronic, and then talk a bit about our journey in the space, I guess. I mean, we're not a space company traditionally. We come from a background of comms and defense work, but we've moved very rapidly into that space in the last 2 or 3 years. I'm going to go a bit through that and how we took some steps into that and some of the stuff we're doing that's really interesting now in terms of really high power amplifiers that we're using to replace traveling wave tubes in ground station applications for space. So here's the mini introduction, I guess. A lot of you will know Filtronic. I guess we've changed a lot over the years. We've been through a big journey from one end to the other for 40 years. And again, we're on another growth spurt at the moment, as I said, and mainly buoyed by that space business that we're seeing. A real change in the space market, I think, in the last five years with these mega constellations that have come along. And we're sort of riding on the back of that, I guess, with these novel solutions that we can do high volume and lower cost than most companies can do. So we're really at the forefront of that. And really pushing boundaries, I think, now in sort of frequency ranges that we're covering as well. So we're covering really high frequencies, mmWave, up to over 100 gigahertz, and really high power amplifiers at that sort of frequency. It's really quite novel technology. Other markets that we serve, I mentioned comms. We're still playing the comms market. And in that market, we do backhaul solutions. We tend to do point-to-point wireless links at mmWave. So typically E-band at the moment, 71 to 76 gigahertz. We have a roadmap now to W-band, which is coming very soon. We have initial devices at W-band that we're using for telecoms and actually for space as well at the same time. And then a roadmap to D-band eventually at 150 to 170 gigahertz, looking at very high data rate stuff for maybe 60. I think we're somewhere off D-band at the moment. It's always coming, I think, is the answer for these things. But I guess what we've seen in the telecoms market is a bit softer than we'd like for 5G, and the rollout's been a little bit slower than everyone would like. I think that's been seen across the market. And I guess that's driven by application space. People aren't using any more data than they did before. So 4G is probably good enough for most people. If we have a good 4G connection, then nobody's willing to pay extra for that 5G connection. So we're still serving that market. I'd say it's a little bit softer, but we'll continue to serve that market as we play in the other spaces. I think our core market focus going forward though will be space, and it'll be defense as well. So defense is another interesting business for Filtronic. Obviously UK-based designer and manufacturing of RF and microwave components, basically covering anything from hundreds of megahertz up to 100 plus gigahertz. So real, depth of experience there, both on the design side and the manufacture side for the defense market. So we have two sites that cover high security manufacture and could be used for that sort of purpose as well. But anything to do with RF, as I say, so basically anything from the antenna, we don't do antennas, but anything before that, and anything back then to the sort of IQ baseband type approach, everything in between we do, so converters, power amplifiers, LNAs, and that sort of thing. So a bit on the recent growth. So I guess a couple of years back, we were about £16 million company and had been for, I guess, a number of years. We grew to 25.4 million last year, so it's got a big increase. And this year, the market prediction is about 40 million. So we've gone through that pretty rapid speed of growth in the last couple of years. That's never easy to do. In terms of employing staff, so I think we've taken on about 20 engineers in the last 6 months, but starting to run out of people. So we need more people. So if anyone's listening who wants to join Filtronic, then talk to me afterwards. But we've got multiple sites, got 3 sites in the UK now. So we've got a site in Sedgefield, that's our main manufacturing site and main head office. We also have a site in Leeds, near the airport. We have a site near Manchester, and we're just about to announce something down south, so we'll keep your eyes peeled for that. We'll have another office coming down south soon. And in our head office, we actually move into a new facility, so to sort of grow with the business, we need to move premises. So you can see there on the map, we've got a new phase of net parks on the same park. We're taking a new building. We should be in there probably Q2 next year. And within that, we'll have 26,000 square foot of manufacturing area and about 6,000 square feet of clean room space. That's about 6 times larger than we have at the moment. So really growing that manufacturing capability and growing the number of lines. So I think we've gone from 3 manufacturing lines, which should, by the time we move in, have about 5. So we're really growing again that manufacturing capability and the ability to scale that volume up. So the first steps in space, I guess, began before I started. I started about 3 years ago at Filtronic. This is going back in time, probably 5 or 6 years ago. And the first thing we did was actually work with some of the companies leading into HAPS, so high altitude pseudo satellites. It wasn't a satellite business that didn't really exist in any great form at that point. But people were starting to do HAPS and look at things like balloon mounted parts or fixed wing platforms. And we started to get involved in that with some of the Californian companies working on that. And there's an example of transceiver that we did with one of the companies. That was actually a dual band E-band module. So it did high band and low band, 71 to 76, 81 to 86, and it could cross between either band. That was because the balloons were moving. You never really knew where you're going to be. You had to be able to swap between the bands. And we actually did a demonstrator with them. And that gave a ground to air link of 40 gigabit per second. So really high power, high frequency link from ground to air. And that was a world record at the time, which was claimed by their engineers, but actually delivered mainly by the guys at Filtronic, to be fair. So I guess what we saw with the HAPS market was it wasn't maybe mature enough, and we still haven't really seen that take off in any massive way as yet. I think the business case is a bit tricky, perhaps, to be honest, and the use cases are a bit more limited than they are for maybe the satellite constellation type work that we're doing now. And then we had this massive sort of burst onto the scene of LEO satellite constellations, and led by Elon Musk and his Starlink constellation. And that's a really powerful piece of work he's done, and they've really driven the pace of change in that market. And it's a massively changed market now to where we were 5 years ago. And it's really been disrupted, I guess. So that probably is a viable market, I think, and there's a number of reasons for that. Connecting the unconnected is really up there on most governments' wish lists. They want to try and connect more people, and there's big swathes of the world still unconnected, particularly in big countries like the States, where you have pretty distributed populations. There's still a big digital divide within the countries. So really driven by government pressure as well. Reduced launch costs. So again, the likes of Starlink and their launch vehicles really cutting the cost of getting into space, and really driving that ability to really lower the cost and push down those cost barriers that we had before. Disaster recovery, another good application for things like satellite. We've seen even in war zones, the importance of satellite now already on the battlefield, given that ability to communicate anywhere, anytime. And defense applications, as I said, there's a significant driver. That's really pushing again, driving a lot of these constellations, a lot more of these satellite constellations coming along, driven by partly that defense background. And I guess a part of the future mobile network is really important as well. So trying to join up the terrestrial network with that non-terrestrial network, and try and we have a true mobile network that works everywhere. And we're seeing massive strides there again, multiple companies, AST and others pushing that direct to mobile, direct to cell from satellite. So really interesting applications coming out for these satellites. So what do they need to be able to do it? What do they need to close that business case? We talked about 5G earlier on, and the fact that that's not really got the business case yet. You look at the customer pull. They really need for these satellites orders of magnitude cost reduction. The old space way was very high cost, very large programs, very big satellites, geo orbit, and they took years and years to generate. That needs to flip on its head. They need to come to different companies. They need to take a different approach and come to companies like us. And we started our business, as I say, in the point-to-point market. We have all that technology. We have the volume capabilities. We have the ability to work at millimeter wave, very high frequency. And we can leverage that capability then to push into that space market. That's what we've seen and why people are coming to us to work with us. Reliable and scalable technology. So again, I mentioned that volume piece, really important to be able to actually drive volume now through it. It's not one satellite, it's not 10 satellites, it's maybe thousands, tens of thousands of satellites. And that's a lot of hard work to get a good quality product out. Then they want higher bandwidth feeder links. So existing feeder links tend to be KU or KA band. And really we're seeing this drive now into higher frequencies, driven by these big mega constellations with broadband data requirements. Pushing into QV band and up to E band. You can see I got down the bottom of that slide there. Some of the sort of bandwidths you can get at these different frequencies. So the KA band, 3 gigahertz on the uplink and a gigahalf on the downlink. By the time you get to E band, you've got 5 gigahertz in each of those bands, the uplink and downlink. So really starting to push that data rate really up, really high. And it's a big requirement. You've got a lot of users in these systems, particularly on the uplink side. You need a lot of data to travel through the satellites. So a bit about SSPAs versus TWTAs. So I think I mentioned we're trying to oust the TWTAs. So at the moment, particularly at the higher frequencies on the ground, so QV band, E band, W band, most of the solutions are TWT. That's because they work better at higher frequency and higher power. So that's the fallback position. But some of the technology benefits of SSPAs, obviously, they're semiconductor devices rather than vacuum tubes, which means they're less complex to make. And that's the really big thing, I think. You know, TWTs are not easy to make. They take a long time to make, and that tends to make them very expensive. Obviously, semiconductors work for a longer lifetime as well, so they can last for a program. You know, we were seeing with TWTs quite often in a 15-year program, they need to be replaced at least once within their lifetime, whereas semiconductor devices, as long as they're kept at a good temperature, can last many more than 10 years, actually. And we're starting to drive that change, I guess, at mmWave, partly driven by semiconductor technology. So we're starting to see the likes of GaN technology coming out that lets us to scale that power density of the devices away from gallium arsenide, where you get maybe 1 watt per chip, up to maybe 4, 5, maybe even 7, 10 watts per chip. That makes a massive difference in what we can do in terms of output power. And I'll cover some of the powers we're covering at that higher frequency later on. Efficiency is not quite so good on solid state compared to traveling wave tubes. You do get slightly better efficiency on the tubes. So the running cost is an impact. So when people balance these systems, you know, you have to look at costs overall, and the electricity costs of running these things are a bit higher for the semiconductor devices. But you have that low maintenance piece as well, so you don't have to replace stuff quite so often. And probably more rugged. I think they're saying, I guess, mainly for spacecraft rather than the ground side, but they're actually more rugged, obviously, because again, tubes are more sensitive to shock and vibration. So part of the answer is custom high-performance mimics, and at Filtronic we have the ability to design mimic devices, and we have our own chipsets. We tend to own that. That started with the telecoms business because we had to. I think in the telecoms business, the cost margins are so low, we had to have our own parts. I guess we're finding very similar actually in the space industry. You know, it's become a very cost-sensitive market. The cost is under pressure. It's not the same market as it was before. But also it gives us other benefits as well. So best-in-class performance, you know, so we can design a particular IC for a particular application. So we can design exactly what we want and get the best performance. Also, improved module yield is really important as well. I'm going to talk a bit later on about combining devices and combining multiple mimics. If you're going to do that, you need to match the mimics pretty well. They need to be well matched in terms of phase and amplitude. So if you have your own chipset and you're doing your own wafer runs, you can pick devices that are very similar together and actually get better performance until the yield overall for that device. So I'd say we're working at V-band, 47 to 52. We're doing E-band devices, 71 to 86, W-band, 92 to 114. And we have all those chipsets available already. So our first W-band chipsets are out already. We have a V-band GaN run out already as well. And then a roadmap later on to 130 to 175. I think we're too early on that for at the moment. D-band semiconductor device technology is not really there. The best you can do in terms of mimic output is probably about half a watt at D-band, and that's using indium phosphide on boutique processors, you know, so quite expensive and probably too expensive, definitely for the comms market, but probably also for the space market. But gallium arsenide has been key to date, you know, really at these high frequencies at E-band and W-band, gallium arsenide was the only way. We're starting to see now fabs open up 90 nanometer processors, 50 nanometer processors, which will get to E-band and to W-band and beyond. So, you know, we're starting to see this processor now start to open up and become commercially viable as well. So they're actually pretty cost effective. So onto the combining then. So we still don't have enough power, basically. So each mimic can only provide maybe a few watts. So if we take E-band as an example, so if you have a GaN device at E-band, you may get 3 or 4 watts per mimic. We're actually driving towards actually wanting maybe more like 50 to 70 watts for LEO, and probably something more like 250 watts for a geo application. So we need to combine lots of devices, and that's the technology we've been working on at Filtronic. And this isn't my work, but some of the work the engineers have been doing at Filtronic. Some very clever work in terms of waveguide combining. And this is very, very low loss waveguide, magic T type combining. So lots of effort goes into the design to get good return losses and very, very low losses. So only a few tenths of a dB basically combining loss in a 32-way combined device. So really quite impressive performance at these high frequencies. As you move towards GaN, there are some other problems to solve. Obviously, the higher power density means you've got higher power within your amplifier. You have to get that heat out. But you also have to look at things like the terminations with a magnetic T. You're not going to match perfectly all the devices. They're going to start to dissipate quite significant amounts of power and heat. And if you're not careful, you can melt terminations within the device. So you have to think a bit differently when you move the GaN and how you design these things as well. So the other thing that's really important, as I said, is cost. So now, how do we do these things? How do we do these very high frequency developments while maintaining a very low cost base? I think part of that is down to our supply chain. We've got a very robust supply chain. We've developed that over many, many years in telecoms, where we've shipped hundreds of thousands of transceivers into the mobile backhaul network. So we have a very strong relationship with our supply chain. And we have very good partners who can do high tolerance metalwork, milling and machining, for example, which will give you that very high tolerance waveguide combining that we need. We've also worked very closely with PCB partners to allow us to use like standard softboard technology, but at these very high frequencies, so we can actually start to develop very low cost but high performing devices, which not many people can do. And then we have to develop advanced assembly processes as well. So the process is really important. So again, at Filtronic, we don't only design and manufacture. We have a very strong process engineering team who optimize all these processes. They work with the design team hand in hand to design for manufacture, and they work hand in hand to hand that product over to manufacturing, so we can have this pain-free, high-yield, optimized performance when we get into production. Now, these are videos. I'm not sure they're going to play. I never put videos in my slides. Rob managed it. I'm not going to even try. I'm going to just skip over that and just pretend they don't exist. This was Finn's idea anyway. It was never my choice, Jerry. So I'm not going to play them. So I just wanted to go through some of the hybrid manufacturing capabilities that we have. So we got full automated epoxy and solder dispense, and we've got this deep access epoxy dispense capability, so you can go into quite deep recesses for power amplifier devices. Very high accuracy, so 35 micron, and a repeatability of 15 micron within that. The die and component attach technology, so the epoxy, eutectic attach, silver sintering. So again, all these processes depend on what you're actually trying to do and the power levels you're trying to dissipate, the thermal characteristics we have, but we have all these different capabilities within Filtronic. Automated die attach lines, and then again, very high accuracy needed for these high frequency applications. So at E band and W band, you need micron level placement accuracy on these die and the die attach. And then wire bonding. So we have fully automated ball bonding, wedge bonding, and ribbon bonding now within Filtronic. So we've upped that capability recently above and beyond to give that wedge bonding as well as an automated service. That helps again with repeatability. So we go back to sort of Rob's presentation on repeatability and doing things over and over again. The wire bonds, again, when we get these very high frequencies, are really important. It's really important to have the same the wire bond length, but also the wire bond shape. Everything impacts the performance and the parasitics of that wire bond and the overall performance of a device. And when you're, again, trying to combine 32 mimics together, every slight difference in the performance of each mimic really has an effect on the output power you get at the end of it. In terms of packaging, well, this is slightly off topic for this one, but we do plastic packaging. We have a full QFN packaging line. We have air cavity packaging and hematic packaging as well within Filtronic. So we cover that broad base of different packaging solutions. And we're starting to see that used now within the space market as well. So people are coming to us for design and build of, say, QFNs for space applications and phased arrays as well. As I said before, we have a roadmap to move into GaN. At E-band, we expect that 20 watts to become something like 70 watts with a 32-way combined device. So we're starting to see that push now into higher frequencies and higher powers. And again, driven by that desire to replace everyone's TWTs. And I think ideally people are looking for about that 70-watt PSAT level for a LEO type application. And as I say, pretty much as much power as they can get for the GEO, but 250 watts to 500 watts is typical. So the V-band SSPA is in design at the moment. We expect to get to production released the end of 25, so next year. And we're working on GaN devices now for that. We've had the first one out recently. We've got a number of different devices going in different fabs to find the best possible mimic process at the moment. But we're expecting on that one to get about 100 watts per Cirrus 32. So 32-way device will give us 100 watts of V-band. So that's 47 to 52, I think. Yeah, 47.2 to 52.4, which covers basically the typical comms band, commercial comms band, plus the defense band as well. And then move into higher power still, combining multiples of these 32-way combined devices into a single output. So they want They want more power. Everyone wants more power. So we're looking at solutions that combine either 4 of these Series 32s or 8 of these Series 32s to give either 250 watts or 500 watts of PSAT using solid state power amplifiers. So if we compare that to what's on the market in TWTs, you can get a 250 watt V-band TWT. There's only one manufacturer of the fundamental TWT underlying that, it's from NEC, and everyone else is repackaging that one device. That's the only thing on the market at the moment, and will cost you about £250,000 per tube. So it's a very expensive way to go. As the only player on the market, we're hoping to cut that cost and provide that benefit in terms of semiconductor performance, long life, all the things I talked about before. So to do that, you need a driver amp, you'd need a smaller Series 5 amplifier, got a Series 4 there. So again, these things scale. We've got 32-way devices, give you lots of power. We do anything from a Series 2 to 4, an 8, a 16 and a 32. So you can scale that power right across the piece, depending on what you require. And then obviously provide driver blocks to drive bigger amplifiers as well. So as you step up in power, we just combine some of our existing devices as driver amplifiers. That's just a quote from the guys at Starling Engineering. So some nice things said about Filtronic and our ability basically to scale and ramp with them. And they told us that they don't have many suppliers who can do that. And we're very lucky to be able to announce that we had that partnership with SpaceX. They don't let many suppliers do that. I think that's fundamental to the fact that we work so hard with them. And we have such a unique capability here in the UK, in the north of England, at these very high frequencies and very high volumes and the ability to scale that pretty much nobody else can do. I think it's true to say if SpaceX could do it themselves, they would. I think that they do everything themselves in-house if they can. They're very vertically integrated. And the fact that they come in to us is testament, I think, to the engineering prowess of the guys at Filtronic, what they're doing there. So a little bit on what's next. So the payload side, I guess, is next. We've worked in the ground station first. That's the easier bit to do in the space market, obviously, because you don't have to space qualify things. You don't have to start radiation testing things, which becomes very expensive and very time consuming. But we have started an ESA project, ESA funded project. That was started last June. I went through the pain of trying to submit the application. So I've got the battle scars of the 100+ page document we had to put together to get the bid. But they do provide really fundamental, life-changing sums of money. So they do actually give that very strong support. And they give 3.7 million euros of a 5 million euro project that we pulled together. So it was really fundamental support. At the time, we'd never have done it without the support of ESA. We'd never have done that project. We wouldn't have had the capital funding internally to do that. So they really give us that launch pad to get the next stage, which is payload. And in that space, we're developing Ka-band transmitters and receivers. So 17.8 to 19.3. And 27.6 to 30 gigahertz, and then Q and V band transmit and receive as well. So 37.5 to 40.5, and 47.2 to 50.2. And we're looking for sort of about 7 watts of output power from the payload side. So obviously it's an asymmetric link, so we're looking for maybe 60 or 70 watts on the ground, and we've got about 7 watts coming back down. And that's because of the asymmetric route of the data. All the data is going up like it does in broadband. You tend to download more than you upload. So they need to say asymmetric links. You don't need quite as much power for the payload side. That's progressing well. We've been doing that for a year. We've got another year to run on that. That'll get us to engineering models. And after that, then we're hoping to take that into product. And we're seeing lots of interest now in that market. We're seeing lots of interest from all the primes, lots of interest from new constellations, and they almost pop up on a monthly basis. You know, someone else is doing a constellation, they're coming and talking to us because we have that critical capability at the really high frequency end of the market. So the really broadband, high data rate links, people are coming to us and saying, can we help them? Can we drive down the cost? Can we do something novel for them? Finally, I think I'm getting close to time, Helen, am I? Yeah. Finally, final slide, pretty quickly. The space roadmap, which looks fairly crowded. I tried to group this into different things. So the bottom third of that is support and development. That's really all the chipset development. That's all the development of the GaN mimics for E-band, for V-band, the W-band PAs that we're doing on gallium arsenide at the moment. Converters as well. So we're looking at doing stuff on the payload with converters. And then also SSPA linearization. So again, as we move to GaN, I'd mentioned some of the sort of instant thermal issues we have because of the power density. GaN also tends to be a bit more nonlinear. It tends to have soft compression. So we need to have linearization then as well. So we're looking at analog predistortion using diode technologies to try and compensate for that and let us drive that harder for the same linearity. We're trying to get as much linearity as possible, so a little back off as possible from that PSAT to give us linear performance so we can transmit higher rates of modulation, basically. On the top is all the ground stuff. I've mentioned most of it already. So Cirrus V-band GaN, a Cirrus E-band GaN is on there, a Cirrus W-band. These are all these 32-way combined devices. The integrated V-band is the multiples of those combined into one. And then obviously you can combine them with converters as well. So we have E-band converters, we have V-band converters that we can add into that ground segment stuff. So we can do all the converters, anything from IF, again, up to the high frequency. On the payload side, I mentioned the K-band, the QV-band stuff we're doing at ESA. We're also developing internally some E-band technology for payload as well, and some W-band technology. So that's the next generation above Q and V-band. I'd say most of the market interest is from Q and V-band at the moment. We're starting to see that push up from K-band, the QV-band. Beyond that, I think time will give us E-band and maybe the higher frequencies as well. And that's it.
Thank you very much, Tudor. A fascinating talk. I was especially pleased to hear magic teas mentioned, because that gave me a flashback to my early career about 45 years ago, designing with those. But yeah, we've got time for 2 very quick questions.
You say you're designing amplifiers but not getting involved in antennae. However, in this era of phase arrays, surely the two integrate together much more closely than those. Are you going that way?
So these are typically reflector based. So these are one output driving a reflector. So these will be typically disk based. We are looking at phased arrays. We don't tend to design them internally, but we work with others who do. And obviously they do impact, like you say, each other. They do load pull each other. They do interact as well when they do that. So it's careful system modeling, I think, when you get to that point to really understand what the devices are doing and how they impact each other.
I think that taking a holistic approach to the two can give you benefits for both. Maybe we should have a chat.
Yeah.